Did you know that the first ever Mars rover was built in the Soviet Union and landed on the Red Planet in the year 1971?
There's a planet in our solar system that has captured human imagination for longer than almost any other object in the night sky. Ancient civilizations tracked its reddish glow across the heavens and built mythology around it. Early astronomers pointed their first telescopes toward it and saw surface features that sparked decades of speculation about canals, civilizations, and life. Science fiction writers populated it with intelligent beings. And for most of recorded human history, everything we thought we knew about Mars was either wrong, incomplete, or simply invented. Then we started sending machines there. And everything changed. Over the past 5 decades, NASA has conducted one of the most sustained and scientifically productive exploration campaigns in the history of our species, progressively peeling back the mysteries of the Red Planet 1 mission at a time. From the first grainy photographs of an ancient, cratered surface to the sound of a helicopter flying through a Martian afternoon, the story of how we came to understand Mars is also the story of how human engineering and scientific ambition evolved together. Each discovery creating the foundation for a more ambitious question, each technological breakthrough enabling measurements and observations that the previous generation could not have imagined. Today we are going to tell that story from the beginning. How do we go from knowing almost nothing about the surface of Mars to driving cars across it, drilling into its rocks, recording its sounds, and now flying aircraft through its skies? How did each generation of Mars exploration build on the last? And where is this extraordinary journey taking us next? The full story of how NASA changed everything we know about Mars begins not with a rover or a helicopter, but with a lander sitting on a rust-colored plane, listening to the silence of an alien world for the very first time. Before any rover ever turned a wheel on Martian soil, before any drill bit broke the surface of Martian rock, the first challenge was simply getting there and surviving the landing. Mars had defeated numerous spacecraft before any mission successfully reached the surface intact, and the history of early Mars exploration is littered with failures that underscore just how unforgiving the Red Planet could be. NASA's Viking program, which placed 2 landers on a Martian surface in 1976, represented the first genuine scientific examination of Mars from ground level. The 2 landers, Viking 1 and Viking 2, were not rovers. They did not move. They sat in place, instruments extended, and measured everything within reach. But what they measured and photographed transformed our understanding of Mars in ways that no telescope observation from Earth ever could. The Viking landers returned the first detailed color photographs of the Martian surface, revealing a landscape that was simultaneously familiar and profoundly alien. The sky was not the deep black of space or the reassuring blue of Earth. It was a pale butterscotch, tinted by fine iron-rich dust suspended in a thin atmosphere. The ground was strewn with rocks of every size, from pebbles to boulders, scattered across a reddish-brown plain that stretched to a horizon noticeably closer than anything you would see on Earth due to the planet's smaller diameter. It looked like the American Southwest on a bad day, dry, cold, windswept, and empty of anything obviously alive. The soil analysis conducted by the Viking landers produced results that have been debated by scientists ever since. The chemistry experiments designed to detect signs of biological activity returned results that were ambiguous at best and misleading at worst. Positive signals that initially excited the science team, but were eventually attributed to chemical reactions involving highly oxidizing compounds in the Martian soil rather than biological processes. The question of whether Viking detected life on Mars, or merely unusual chemistry, remains technically unresolved to this day, though the scientific consensus leans heavily toward the non-biological explanation. What Viking definitively established was a baseline understanding of Martian soil composition, atmospheric conditions, daily temperature cycles, and surface appearance that every subsequent mission has built upon. It also established something equally important: that landing on Mars was survivable, that instruments could function in the harsh Martian environment, and that the planet had stories to tell if you could get close enough to listen. 20 years passed between Viking and the next successful Mars surface mission. Those 2 decades were not idle. NASA studied the Viking data, developed new technologies, and worked through the engineering challenges of sending not just a lander but a mobile vehicle to another planet. The result arrived in 1997 aboard the Mars Pathfinder mission, a small, 6-wheeled rover named Sojourner that would capture the imagination of the entire world and establish the template for everything that followed. Sojourner was modest by any measure of what came later. It was roughly the size and weight of a microwave oven. It moved at a maximum speed that a determined tortoise could have matched. Its scientific instruments were limited compared to what modern rovers carry, and it operated for just under 3 months before communication was lost. But it accomplished something no machine had ever done before. It drove across the surface of another planet, picking its own path around obstacles, examining rocks up close, and sending back data that scientists could not have obtained any other way. The engineering foundation of Sojourner was a suspension system called the rocker bogie, and it was one of those elegantly simple mechanical solutions that turns out to be nearly perfect for its intended purpose. The system uses 2 linked articulating arms connecting the wheels to the rover body, a longer front arm called the rocker and a shorter rear arm called the bogie. The geometry of the system means that as any individual wheel rises or falls to accommodate an obstacle, the movement is distributed across all 6 wheels, keeping the rover body relatively level and ensuring that all wheels maintain contact with the ground simultaneously. On a surface covered in loose rocks of every size and shape, this system proved extraordinarily effective. Sojourner could climb over obstacles nearly a third of its own height, a capability that proved essential on a Martian landscape that the Viking photographs had already shown was anything but smooth. The scientific return from Sojourner was significant beyond its modest size. The rover carried an alpha proton X-ray spectrometer on its front face, an instrument that could determine the elemental composition of any rock the rover was driven up against. By pressing this instrument against multiple rocks during its operational period, Sojourner revealed that the Martian surface contained a diverse range of rock types with chemical compositions that told stories about the planet's geological past. Some rocks appear to have formed in the presence of water. Some suggested volcanic activity. The 3 months of Sojourner's operation generated more questions than it answered, which in science is usually a sign that something genuinely interesting has been discovered. Perhaps more important than any specific scientific finding was the proof of concept that Sojourner represented. A wheeled robot could navigate the Martian surface autonomously, respond to commands from Earth despite the communication delay of many minutes each way, and survive the temperature extremes and radiation environment of Mars for months. The foundation for everything that came next had been laid. If Sojourner was proof that a rover could work on Mars, Spirit and Opportunity were proof that rovers could transform our understanding of an entire planet. Launched in the summer of 2003 to take advantage of the orbital alignment that brings Earth and Mars into their closest approach every 26 months, these twin rovers were larger, more capable, and more scientifically equipped than anything that had preceded them. They were also, by any reasonable measure, among the most successful scientific instruments in the history of planetary exploration. Spirit and Opportunity were each roughly the size of a golf cart, dramatically larger than Sojourner, with the same 6-wheel rocker bogie drive system scaled up to match. Each rover stood approximately 1.5 meters tall at the top of its camera mast, carried 9 cameras for navigation and science, and mounted its primary spectrometers on a robotic arm that could extend outward to examine rocks and soil directly. This arm-mounted instrument package allowed the rovers to conduct close-up geological analysis that far exceeded what the Pathfinder mission had achieved, essentially functioning as a field geologist's toolkit deployed on another world. The scientific discoveries made by Spirit and Opportunity over their operational lifetimes fundamentally changed how scientists understand the history of Mars. Opportunity, landing in a small crater called Eagle Crater in the flat Meridiani Planum region, almost immediately drove over to an outcropping of bedrock and found something extraordinary. Spherical concretions of a mineral called hematite, nicknamed blueberries by the science team, that could only have formed to prolong exposure to liquid water. Further examination of the bedrock revealed layered sedimentary structures with characteristics consistent with formation in a shallow saltwater body, similar in some respects to shoreline environments on Earth. This was a definitive evidence that liquid water had once existed on the Martian surface in substantial quantities and for extended periods of time. Before Spirit and Opportunity, this was a hypothesis supported by orbital imagery showing ancient river valleys and lake basins. After their discoveries, it was a confirmed scientific fact grounded in direct chemical and physical measurements made at the surface. Ancient Mars had been wet. The implications for the possibility of ancient Martian life were immediately profound and remain an active area of scientific investigation today. Opportunity operated for an almost unbelievable 14 years and traveled 28 miles across the Martian surface before a global dust storm in 2018 covered its solar panels and drained its batteries beyond recovery. Spirit operated for 6 years before becoming stuck in soft soil in 2010. Together they had rewritten the geological history of Mars, proved that habitable conditions had once existed there, and demonstrated that robotic exploration at the planetary surface could deliver science of the highest quality over timescales that no one had anticipated when the missions launched. The success of Spirit and Opportunity set an almost impossibly high bar for the next generation of Mars rovers, but the mission that followed managed to raise it further still. Curiosity, which landed in Gale Crater in August 2012 using a sky crane descent system so complex and audacious that NASA engineers watching the live telemetry could barely believe it worked, represented a complete reimagining of what a Mars rover could be. Where Sojourner was a microwave and Spirit and Opportunity were golf carts, Curiosity is an SUV. It weighs approximately 900 kilograms, measures nearly 3 meters in length, and carries 11 distinct scientific instruments representing contributions from research institutions across multiple countries. It does not run on solar power. Instead, a radioisotope thermoelectric generator converts the heat released by the natural radioactive decay of plutonium-238 directly into electricity, a power source that operates continuously regardless of dust accumulation, day-night cycles, or seasonal variations in sunlight, giving Curiosity an operational independence that solar power rovers fundamentally cannot match. Curiosity's central scientific objective was different from its predecessors in a subtle but important way. Spirit and Opportunity had focused on finding evidence of past water, proving that liquid water had once been present on Mars. By 2012, that question had been conclusively answered. Curiosity was sent to answer the next question. Had Mars ever been habitable? Not just wet, but genuinely capable of supporting microbial life by providing the chemical energy sources, liquid water, and chemical building blocks that Earth life requires? The answer that Curiosity found within its first year of operation was yes. Analysis of drilled rock samples on the floor of Gale Crater revealed mudstone, a fine-grained sedimentary rock that forms at the bottom of ancient lakes, containing carbon, hydrogen, oxygen, sulfur, nitrogen, and phosphorus. These are the 6 elements that Earth life is built from. The ancient lake that once filled the basin where Gale Crater now sits had been a freshwater environment, not the highly acidic or highly salty ancient waters that some earlier evidence had pointed toward. It was, in the language of the science team, a habitable environment, a place where Earth-like microbial life, had it been present, could have survived and potentially thrived. This finding did not prove that life had ever existed on Mars, but it established definitively that Mars had once offered the conditions necessary for life to arise, bringing the possibility from speculative to scientifically credible in a single drilling campaign on the floor of an ancient crater. The Mars 2020 mission that delivered the Perseverance rover to Jezero Crater in February 2021 carried with it everything that had been learned from every previous Mars surface mission, and then added something genuinely new. Tucked beneath the belly of the rover, attached to the underside, like a passenger waiting to disembark, was a small helicopter named Ingenuity. And the moment it lifted off from the Martian surface for the first time on April 19, 2021, it became the first powered aircraft in history to achieve controlled flight on another planet. Flying on Mars is an engineering challenge of extraordinary difficulty. The Martian atmosphere is less than 1% as dense as Earth's atmosphere at sea level. To find an equivalent air density on Earth, you would need to ascend to an altitude of approximately 87,000 feet, nearly 3 times the cruising altitude of commercial aircraft and far beyond the altitude record for any helicopter flight on Earth. Everything that makes helicopter flight possible on Earth, the lift generated by rotor blades, the control authority provided by varying blade pitch, has to be completely reimagined for an environment where there is almost no air to push against. Ingenuity's solution involved rotor blades specifically engineered for maximum lift efficiency, rotating at approximately 2,400 revolutions per minute, roughly double the RPM of a conventional helicopter rotor. The 2 counter-rotating rotors, stacked one above the other on a single mast, eliminated the need for a tail rotor to counteract torque. The entire vehicle was stripped of every gram of unnecessary mass, cameras, a solar panel, and a small battery pack were the primary systems beyond the rotors themselves, resulting in a machine weighing less than 2 kilograms. Ingenuity was originally planned for just 5 experimental flights. It completed 72. Over nearly 3 years of operation, it accumulated more than 2 hours of flight time and demonstrated conclusively that aerial exploration of Mars was not just possible but practical. The data and imagery it collected from altitudes impossible for ground-based rovers to replicate opened a new dimension of Martian science and reconnaissance. Perseverance itself has continued the geological work that Curiosity began, this time with a specific objective of collecting and caching rock and soil samples for eventual return to Earth, the most scientifically valuable mission objective in the history of Mars exploration. Dozens of sample tubes, each containing carefully selected core samples from ancient Martian rock, have been sealed and deposited at the surface, waiting for a future retrieval mission that will bring them back to Earth-based laboratories where a full suite of modern analytical chemistry can be applied. The trajectory of Mars exploration over the past 50 years points clearly toward where we are headed. Sample return missions in the 2030s will bring ancient Martian rock to Earth laboratories for the first time, where analytical capabilities far beyond anything that can be miniaturized into a rover instrument package will probe those samples for biosignatures, chemical or physical evidence of past biological activity, with a sensitivity that current surface instruments cannot achieve. Future aerial vehicles, building directly on Ingenuity's success, will extend the reach of Mars exploration dramatically. A next-generation Mars science helicopter currently in development would carry scientific payloads and cover distances in a single flight that current rovers require years to traverse. The combination of surface rovers and aerial vehicles working together, coordinated by increasingly sophisticated autonomous navigation systems, will enable exploration at a pace and scale that no previous generation of Mars scientists would have considered possible. And behind all of this science, of course, lies the ultimate destination that has been implicit in every Mars mission since the beginning. Human beings, standing on the surface of the red planet, looking up at a pale sky, and beginning the work of understanding a world that generations of robots prepared for their arrival. The story of how NASA changed everything we know about Mars is ultimately a story about the compounding power of sustained curiosity. Each mission answered the questions left by the one before it, and in doing so, generated questions more profound and more interesting than anyone had thought to ask at the beginning. We went from not knowing what the Martian surface looked like to driving cars across it, from not knowing whether water had ever existed there to identifying the specific ancient lake beds where it once sat, from wondering whether Mars had ever been habitable to confirming that it once offered every chemical condition that Earth life requires. From confining our exploration to ground to lifting a helicopter into a Martian sky. Every one of those steps was taken by machines built by human engineers, guided by human scientists, funded by the collective investment of human civilization in the project of understanding where we live in the universe. And the machines currently operating on Mars right now, drilling, flying, caching samples, measuring, listening, are laying the foundation for the next chapter, the chapter where we go ourselves.